everyone. Sorry I had to cut out right in the middle of a proof yesterday, or last night. I just had a little bit of a time constraint. So sorry about that. I want to pick up right where we left off. So let me just remind you what we had. So I'll just kind of write the last few sentences of where we were last time. So we had that L contains an nth root of unity, which I called epsilon, and then we defined L, what did I write? L sub I prime. That was equal to L sub I adjoint epsilon. And so that gave us this chain, this tower. So this gives us, so it would be K contained in L0 prime, contained in L1 prime, dot, 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 contained in L sub M prime, which was equal to L. The reason, since epsilon is inside L, when you join it, you just get L, right? You don't get anything new. Okay, so now let's jump into step 3. So this was the end of step 2. Now we're on step 3. So what we want to do is show that gamma of L over K is solvable. Or I guess I should probably say we show that gamma of L over K is solvable. Okay, so let's just remember, so recall that, so I want to look at the mapping gamma, right? That goes from script f hat to script g hat. And remember, one of the properties that it has, it's inclusion reversing. So this is inclusion reversing. And so we have, right, okay, so now what I want to do is I want to apply gamma to each one of these in this chain right here, and so then the containment is going to go in the opposite direction. So this will give us 1, which equals gamma of Lm, do I want to put an L? Yeah, okay. L over L sub m prime, right? L is equal to L sub m prime, so this is the Galois group of L over L, right, which is trivial. Contained in, and I guess I could use, I'll use subgroup symbol here, so contained in gamma of L over L m minus 1 prime, contained in dot, 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 contained in, and then the last one I'm going to end with, do I use L0 here? Yeah, and I wonder, yeah, that's okay. Contained in gamma of L, over L0. Sorry, over L0 prime. All right, so what do we want to do? We want to, right, we're trying to show that this group right here is solvable, right? So we're going to need some kind of chain like this. All right, so you can see now this chain leads to this chain, and we're going to show normality and so on. Okay, so the next step here, viewing the polynomial, it's going to be x to the n sub I, x to the n sub I minus theta sub I. So viewing that as a polynomial in L sub I minus 1 prime, bracket x, right, L sub I prime, which equals L I minus 1 prime adjoin beta is the splitting field of this polynomial. Of this polynomial over over L sub I minus 1 prime. And I want to just label this sentence, label it star, because I'm going to refer back to it in a sec. Now, it follows that the Galois group gamma over L sub I minus, L sub I prime over L sub I minus 1 prime is cyclic, and we can actually specify who the generator is. So generated by the mapping that sends beta sub I to beta sub epsilon sub I beta sub I. All right, so that mapping then generates everything in this in the automorphism group. Okay, so now by the fundamental theorem, so fundamental theorem of Galois theory, phi of gamma of L over L sub I prime is equal to L sub I prime, and phi of gamma of L over L sub I minus 1, L sub I minus 1 prime equals L sub I minus 1 prime. Now, the extension so now L sub I prime over L sub I minus 1 prime, this is normal because it's a splitting field. Right, so this is by star. And so gamma, get this right here, gamma of L over Li prime is a normal subgroup of gamma of L over L sub I minus 1 prime. Okay, so what does that allow us to do? It allows us to put normal subgroup symbols all the way through that chain right there. Also, we can say exactly who the quotient is. Right, so this is fundamental theorem right there. This is, I don't know, part, I can't remember which part, it's part B, I think, right there. And then, or I don't even want to remember that or say that. Okay, so this, but this is also fundamental theorem of Galois theory. So you can say also, when we look at the quotient, what we have is that gamma of Li prime over Li sub minus 1, L sub I minus 1 prime, is isomorphic to the quotient gamma Li minus 1, L over L sub I minus 1 prime. Oh shoot, I think I need, Oh, no, we're good. L, I don't need an L prime. It's L. So this is L I prime. Okay, mod gamma of L over L sub I, L sub I prime. Now, as we just said, this group is cyclic, which means that we get cyclic quotients, which means abelian quotients. So we can say, therefore, gamma of L over L0 prime yeah, that's the ending point right here, which is equal to gamma of L over K adjoint epsilon is solvable, right? We have a subnormal series here where this is the terminating group, right? With cyclic and therefore abelian quotients. That's not quite what we wanted though, right? We want to show that gamma of L over K is solvable. We don't have that. We got K adjoint epsilon there. So we got a little bit more work to do. So next step, the roots of x to the n minus 1, I think I want to n, yeah, x to the n minus 1 in k bracket x are 1 epsilon squared up to epsilon to the n minus 1, right? And these, or we can say, and so k adjoint epsilon is the splitting field for this polynomial, so for x to the n minus 1 over k. So now, so you can say now, gamma of k adjoint epsilon over k is a finite abelian group where we get one factor, I should say one cyclic factor, for each irreducible factor of x to the n minus 1. So the idea is take x to the n minus 1, split it over k into its irreducible factors. And then what you will have is, so you'll have a bunch of factors, and you can look at, what can you look at? Each of the, I don't want to say this, the Galois groups of the corresponding splitting fields for each of those factors. Each one of those is going to be a cyclic group, and so overall then, this right here, right, will be the direct sum of those cyclic factors. Okay, so I want to label this double star, and I'm going to need that in a second also. Now, abelian groups are solvable, so we can say therefore gamma of k adjoint epsilon over k is solvable. Now, since k adjoint epsilon over k is normal, that's because it's a splitting field. K joint epsilon is a splitting field. This is by, right, so by double star. Gamma of L over K adjoint epsilon is a normal subgroup of gamma of L over K. So, once again, by the fundamental theorem, the quotient gamma of L over K mod gamma L K over epsilon, that's isomorphic. That's going to be isomorphic to gamma of K adjoint epsilon over K. This is solvable, which means that this is solvable. Right? Let's say, and so our quotient gamma of L over K mod gamma of L over K joint epsilon is solvable. Okay, so now what do we have? We have what? We have gamma of oh, now I'm lost. Okay, so let me think. The quotient is solvable. Oh yeah, the quotient is solvable, and the denominator is solvable, and so then we go back to our previous theorem. That tells us that the numerator is solvable. So now, by theorem 6 point something, 6.2b, gamma of L over K is solvable. All right, so now we're ready for the final step in the proof. Okay, so we showed gamma of L over K is solvable. Now we need to show that gamma of F is solvable. So we now show that gamma of F is solvable. So what do we have? So we assumed that F splits over L, right? So let's let sigma be the splitting field for F over K. Then we have that sigma lies in between K and L. And sigma over K is normal. All right, so what does that tell us then? So by the fundamental theorem again, so by fundamental theorem of Galois theory, we can take a quotient, right? So gamma of f, which equals gamma, just by definition, gamma of sigma over k. That's going to be isomorphic to the quotient gamma of L over K mod gamma of L over sigma? Yeah, L over sigma. Okay, so what does that tell us then? It tells us that gamma of F is a quotient of a solvable group by our theorem 6.2, right? So since gamma of F is a quotient of a solvable group, gamma of F is solvable by theorem 6.2. All right, that's the big theorem, and now it's time to work into applying this theorem. Let's see how we're doing on time. Oh yeah, okay. So now I want to kind of build up the machinery. So now what we're going to do is work towards producing a polynomial. Let me fix this, looks a little off kilter. I want to work towards producing a polynomial that's not solvable by radicals. Okay, so there's a little bit more work to do, but this is the big theorem that relates this notion of solvability by radicals, which you can think of as the ability to find a formula for factoring the polynomial that involves just the usual field operations plus taking nth roots. So there's this connection between this solvability of radicals and having the Galois group solvable. Okay, so we need to do a little bit more group theory. So first, a definition, an action of a group G, so of a group capital G on a set capital X is a homomorphism should I use the symbol alpha from G into S of X. Now, the typical notation if little g is in capital G and little x is in capital X, we write G dot X rather than alpha of G of X. So here's the idea. An action of a group is a way to have the group elements behave as permutations of the set. Right? So what do? This homomorphism alpha associates to each element of the group, right, a permutation of the set X. Okay? And what we write is G dot X rather than alpha of G applied to X. And so we'll typically say G acts on X, and in fact, the quick notation is like this: G and then a sort of circular arrow X. This is often read G acts on X. Or there is an action of G on X. A couple of pieces of terminology here. So an action, say alpha, from G to S of X is And then part A of our definition, it's faithful if the kernel of alpha is trivial. Now, in that case, right, if the kernel is trivial, then what can we do? We can view G as being a subgroup of S of X. I mean, yeah, right. We can identify it. So we'll just say this. So in this case, we can identify G, right? G will be isomorphic with phi of G, which is a subgroup of the permutation group of X. And then part B, it's transitive, right? So the action is transitive if for each X and Y in capital X, there exists some little g in capital G, such that G dot X equals Y. A couple of examples of group actions. The group G always acts on itself by left multiplication. That's Cayley's theorem. So Cayley's theorem is that G can always be viewed as a subgroup of the group of permutations of G. Right? G is isomorphic to a permutation group. Another example, if R is the set of roots of some polynomial, let's say f in k bracket x, and f is then we can say it like this way, that then the Galois group of f is a subgroup of S of R, the group of permutations of R, and f is irreducible if and only if gamma of f acts transitively on capital R, right? In which case there's an automorphism of the splitting field that takes any root to any other chosen root. Okay, so now given x and y in x, let's write x tilde y if and only if x equals y, or the transposition xy, right? So that is the permutation of capital X that interchanges x and y. I know I don't want to confuse this with ordered pairs. Okay, just remember, I typically write a little comma in there. So if if the transposition, right, the permutation of capital X that interchanges x and y and leaves everybody else fixed, lives in capital G. Now, you can check, so let's say check, that tilde is an equivalence relation on capital X. All right, so now I'll call this lemma 6.8. So let's let I need an action, right? So I want a finite set. So let's let x be a finite set, and let alpha from g to s of x be an action of a capital G on capital X. Okay, so then, we'll say if alpha is faithful and transitive, then for each, now let's say like this, then the cardinality of any two equivalence classes are equal. So then the equivalence class of x equals equivalence class of y, or the order for each x and y in capital X. So for the proof, so let's pick our two elements. So let's let x and y be in capital X. Now, one thing that you probably remember about equivalence classes, they're either equal or they're disjoint. So if they're equal, of course they have the same cardinality because of the same set, and so we can assume that they're actually disjoint, right? So if the equivalence class of x intersect the equivalence class of y is non-empty, then they have to be equal. And so we may assume that they actually are disjoint. So the equivalence class of x intersect the equivalence class of y is disjoint. Now, we know that alpha is transitive. So since alpha is transitive, there exists some little g in capital G such that g dot x equals y. I think that's the direction I want to go, right? Yeah. Now, okay. So if z is in the equivalence class but not equal to x, so with z not equal to x, then what? Oh, right. Oh, but they're equivalent, right? So that means that, so then we know that xz is an element of G. So it follows that alpha of G times xz times alpha of G inverse is an element of G as well. Okay, but alpha of G xz alpha of G inverse is equal to, so I want to actually write this out. So what would this look like? It's going to be equal to the cycle. So let me do this in steps here. So this will be alpha G of x, which you can write as G. Should I just write it as G dot x? Yeah, I should just write it as G dot x. So this is G dot x, comma G dot z. Which is equal to y, comma G dot z. This is in the equivalence class of y. Oh, wait, did I miss something here? No? This doesn't make sense. This doesn't make sense. That's not an element of equivalence class of y. What is this in? Oh, right, okay. Okay. So this tells us that G dot Z and so G dot Z is an element of the equivalence class of Y. Therefore, well, now I got to write it in this form. Alpha of G of bracket X is contained in the equivalence class of Y. Now, since, remember, we assumed that we had a faithful action, so since alpha of G restricted to the equivalence class of X from the equivalence class of X to the equivalence class of Y is 1 to 1, we have that the equivalence class of X has to have size less than or equal to the size of the equivalence class of Y. Sorry, I got a little crossed up there. For a second I couldn't realize what we were even doing. Okay, so I see what I want to do now. So what we did is we show that this function right here actually makes sense, that it has the right codomain, right? It takes the equivalence class of X into the equivalence class of Y. Then we use one-to-oneness to show this, and the same thing. So similarly, the size of the equivalence class of Y is less than or equal to the size of the equivalence class of X. Okay, so that's the end of the proof of the lemma, right? We just need this group theoretic thing. I guess we'll stop here and we'll pick up this later.